chemical theory. Inorganic chemistry is built on MOs. So you'll see it again. What I want to talk about today now is I want to spend the day talking about molecular orbitals on the N=2 octet period. Right, so starting from sodium and going to neon, right? The N=2 orbitals, and that's where more interesting molecular orbitals start to appear because not everything looks like spheres anymore. Things have direction. So we start to see we're going to start to see some more interesting kinds of behaviors and molecular orbitals that form because we have P's and S's to work with. So that's what we're going to look at today. And let's just start simple, right? Let's start with something kind of basic, not too complicated. That isn't have a lot of let's just take H2 and make it a little more interesting. And let's look at today. Let's look at to begin. Let's just look at nitrogen, molecular nitrogen. Right. I want to kind of explore molecular nitrogen today because it's got it kind of has all the features of the bonding characteristics that we come to expect from the N=2 orbitals, from the P's and the S's, and it has all of the features. So it's a really nice molecule to look at. We don't have to worry about electronegativity either, which is going to change things a little bit. So let's think about again, we know what the electron configuration of this molecule is, are these atoms. Nitrogen are 1s2, 2s2, 2p3. Right, so each nitrogen brings to the table 7 electrons, right? So we're going to combine 2 nitrogens, so we have a 14 electron system. And so we should think about how the different types, and we have 3 different types of orbitals that have 3 different types of geometries. They're all orthogonal inside the atom. And so we should think a little bit about how these may combine. We have choices on how we add orbitals together because we have 3 different kinds. But let's use the tools of ionization energies and things like that to think about where different orbitals of the atoms lie in energy. And what we're going to learn, and we kind of saw this a little bit with hydrogen, is that for two atomic orbitals to form a molecular orbital, they need to overlap together. And that overlap has some, like the general rules of that overlap, it's kind of simple, but the general principle is that 2 atomic orbitals will combine. Let's say, for instance, we have psi A and psi B, 2 different atomic orbitals. They'll combine if 2 things are satisfied. One is that there is some overlap between the 2 functions, which means that the integral over the molecule is not equal to 0. But they have some similarity to each other. They're not perpendicular to each other. They exist in the same space. Like they have some overlap. So that's what we call non-zero overlap. But we could find, again, a lot of different orbitals will overlap. Like, for instance, the 1s orbital will overlap with the 6s orbital. I mean, the 6s orbital, in some sense, the electron is pretty far away from the nucleus. It's going to be around the other nitrogen. Right, so we could say, well, why can't I just combine the 1s with the 6s or the 5s or the 4s, right? Why can't I just make any combination? I can. There's nothing wrong with that, creating that, but those combinations don't contribute very much, right? I don't expect to see a molecular orbital between the 1s orbital of one atom and the 4s orbital of another one. That just isn't going to happen. And so that we can say what the criteria that satisfies this is, which is that the 2 orbitals that mix, their energies have to be fairly similar. So what I should say is that the energy between the 2 orbitals, so the difference between the energies, should be close to 0. right? They're not exactly zero, but they should be close, right? So orbitals of like energy will mix. Okay, so that helps us. That means that if two orbitals and two different atoms are very different in energy, I don't have to worry about the combination. They're only going to combine close to each other. And we can think about that as overlap. These are in some sense saying the same thing in some ways. If one of the atoms is in the 6s, that's great. There's some overlap. But the wave function oscillates a lot, right? Every time you increase the n on any quantum mechanical wave function, you create a wave that's higher frequency. So it's going positive, negative, positive, negative, positive, negative a lot more. Remember, the 1s orbital is just a positive function. So they cancel each other out a lot. So these kind of connect, right? It tends to be that orbitals that are close in energy have good overlap because they don't oscillate so rapidly. So that's a consideration that we have to make. There's a balance of the two. So we should look at where the orbitals of nitrogen lie and just match the orbitals that are similar in energy. So let's start with the core. All right, we have 1s2. Let's think about where those electrons lie in energy relative to ionization. They're going to be really, really deep, right? Because they're very close to a very positively charged nucleus, right? With nitrogen it has 7 protons. So these are extremely close to the nucleus. They feel a ton of attraction. So they're very deep in energy. Each electron experiences effectively 49 times the attractive force from the proton or the nucleus that the hydrogen atom does. So it scales as the number of charges squared. There's 7 versus 1. That's a factor of 49. So those are sitting deep, deep, deep down. And if you go look at the ionization potential for these, the ionization potential, which again is the amount of energy I need to put in to kick them out, is greater than 100 electron volts. Remember, in hydrogen, the 1s1 electrons at minus 13.6. So this is almost 10 times deeper in energy, 10 times more hardly bound. Right, so they're bound for 2 reasons. One is that the nucleus attracts 49 times stronger than hydrogen. Right? The difference is not 49, it's not 13 times 49, it's 100. That's only 10. And the reason why it's not so deep is that it's also being repelled by the electrons above it. So there's a core of electron, there's a valence of electrons above it in some sense in the higher shell that's also repelling it. Okay. So what that means is, so we just have to see where the 2s electrons are. And maybe we don't even have to worry about the 1s's, they're just going to be on their own. So let's look at the 2s. And this is, again, this data just comes from NIST. I just look at the ionization levels of nitrogen. And here the ionization potential, right? Let's think a little bit about what the atom inside looks like from the perspective of those electrons. Underneath the valence, there is a core of 7 protons. But underneath it are also 2 electrons, the 1s2. So what the 2s2 electrons actually see is not really a core of 7 charge, but it's a core of 5 charge, because the electrons underneath it cancel out some of that charge. So for these, the effective Z that it feels looks like the number of protons minus the number of core electrons, which is 5, right? So these are less shielded. they kind of make, they're less repelled, they're less attracted than you would expect. But they're still repelled by those electrons there. But effectively, it feels a formal charge of 5 instead. And so the 2s electron will ionize at more of a hydrogen level of energy. They're not going to be quite 13 because they're more attracted more strongly to the nucleus because he is effectively 5 instead of 1, but they're not going to be at 100 eV. In fact, when you go look at the data, you find that the IP of these is just 18 eV. Right? It's slightly deeper than hydrogen, but they kind of look, right? Valence electrons look like valence electrons. And valence electrons have a lot of hydrogenic behavior. That's what we've been looking at, right? The valences can be represented like hydrogens. So this has a very similar value to the hydrogen 1s orbital. Right? And we know that there's again one more level of orbitals. We know how they get filled, right? 1s gets filled, then 2s gets filled. That means that the 2p orbitals have to be higher in energy than the s orbitals. They have to be higher in energy than the s orbitals. They're less stabilized because the electrons are further away. They're going to be bound less strongly to the nucleus. And we know from Hund's rules. We don't know that from Hund's rules actually. But by opt-out principle, we know that 2p gets filled next. So they're going to be higher in energy. And the 2p3 electrons have an IP of 12 eV, right? They look just like they're very close to where hydrogens are. They've been shielded by 4 electrons underneath them. So the effective charge that they feel is 3. So they're even less attracted to the core and less repelled. And so they're even more repelled because there's tons of electrons under them. And so the IP is just slightly above, less stable than hydrogen. But they're all pretty close to the hydrogen value of 14. Right? All the valences tend to fall in the same region. So what does this tell us? Well, this tells us that when we combine electrons together, or atoms together, that the 1s's are going to interact by themselves. But the 2s's and the 2p's, they're pretty close in energy, and so we should see some mixing between them. Right? The p's are going to combine, and the s's may also combine. We know that s's and p's do combine because when we construct carbon with molecular orbitals, we hybridize the orbitals, right? We build sp3 orbitals. And the entire point of that is that we take these p electrons, which are very close in energy in some orbital, and the s electrons that are very close in energy in their orbital, and we just create superpositions of the two to combine them into a set of 4 identical orbitals called sp3 orbitals. And that's perfectly allowed because both of these sets of orbitals are very close in energy. And they're even closer in energy in carbon because carbon has less electrons. So what I should expect is that my molecular orbitals, that I should get a combination of 1s and 1s. I should certainly get a combination of 2s and 2s. And then I might also get 2p plus 2p and maybe 2s plus 2p. Maybe. Right? But certainly the dominant contributors are going to be the p's combining and the s's combining together because they're at the same energy. But the 1s is never going to, the core never touches the valence. But in some sense, we already knew that. That's the whole reason why we talk about valence electrons in Chem, is that we know implicitly that the core electrons of the atom don't contribute at all to bonding. Right? So I know that those aren't going to combine with the valence because we know from Chem that the valence electrons are really the only ones that matter. And that's the reason why. We're just too deep to mix. So let's do the exact same process that we did for hydrogen and think about how these orbitals will combine geometrically, qualitatively. Okay. So let's build a little energy diagram for our nitrogen atoms. I'm going to have 3 columns on this energy diagram. I'm going to zoom out just a bit. There we go. we're going to put nitrogen A on one side, our orbitals for nitrogen A, or orbitals for nitrogen B on this side, and in the middle we'll meet for the N2 orbitals. Okay. So our first orbital is at like minus 100 eV. That's our 1s's. It's 100. So we have some 1s orbitals here. They're 1s2. So we have 2 electrons in them. Right? And we know how 1s is combined. We did it on hydrogen, right? They form a bonding pair and an anti-bonding pair. A sigma and a sigma star. Right? So we get a sigma bond. And we get a sigma star anti-bonding orbital. Right? And now we can fill these 2 orbitals with electrons. There are 4. So both of the orbitals get filled. Right? And so what we have here is a set of molecular orbitals that form with the core, but both of them are completely filled. What that means is that any bonding interaction is completely canceled out by the anti-bonding interaction. So these core electrons contribute nothing to bond. Right? They can form a bond, but there's enough electrons in them that it cancels it out. So again, the core does not contribute to bonding for exactly this reason, because the core molecular orbitals always get filled. So there's no bond here. This is supposed to be minus 100. It does not look like that anymore. Okay. Right, and we have a huge gap in energy now. Right, the next orbital is the 2s, and that is at 18. So there's this whole gap in energy where there is nothing. There's no orbitals. So I can kind of put this here. Right? And then the next set of orbitals, the valence, starts at minus 18. And we have the 2s2 state. And again, they combine precisely the same way. Okay. You can think a little bit about their overlap. They don't bond quite as strongly as the 1s's because they have more oscillations on them, but they do overlap. They're at the same energy. But these orbitals are also completely filled. Right, so at least at the first limit, these 2s orbitals don't contribute at all to this bond. No bond. Okay, and then we're left with the p's, which are at minus 12. Right, so we have 3 equivalent p orbitals and 3 equivalent p orbitals. And each one, right, is half filled. Now we're going to form combinations that aren't going to completely fill up. At least we don't think so. But we should think a little bit about how these p orbitals may combine. These have slightly different geometries than the s orbitals. They're not spherically symmetric anymore, right? They're cylindrically symmetric. They're pointed along one of the 3 axes. They no longer have spherical symmetry. So we need to think about how the 3 different orientations of the p orbitals interact with each other. So let's set up we need to set up a coordinate system so we know where the atoms are, and so we can align the p orbitals. So we'll just do the old school way that scientists like to do, which is to define the bond axis of the system as the z-axis. Right? And then we'll just define the perpendicular axis as x. Okay, so y is out of the plane. So let's think about how the different p orbitals interact. Right, so let's think now, let's first start with the easy ones, which are 2pz. Right, those are the orbitals that are lying along the bond axis in the nitrogens. So we're going to have a nitrogen atom with a p orbital in the z direction like this, where they are of opposite sign, right? Plus and minus. Right? And we're going to add it to our other nitrogen, which has the same alignment as before. I'll just color code it this time. And we can see when we add these together, right, we have a constructive overlap between the two lobes pointing at each other. They're both positive, they're both aligned, and they're going to share. So we have some nice overlap between these. Right? So they overlap symmetrically about the z-axis, right? You get overlap above the bond and overlap below the bond because the p orbitals are symmetric about the bond. They get cut in half like the bond. So we have kind of the same, the bond looks the same regardless of the direction, right? So I can rotate this and I see the same thing. The bond interaction is same regardless of angle. Okay. And this is so it has cylindrical symmetry, this spherical symmetry. It looks the same at all angles around the bond. This is a sigma bond. Right. And we're going to form something, a molecular orbital. Change the colors, I'm sorry. That kind of looks like this. Right, this is our MO. Okay, so we're going to form this sigma orbital where the two PZs add together across the bond. Right, so we can create a little sigma orbital here. Like that. Okay, and each of those PZ orbitals had one electron in them. So they fill up the bonding orbital. Right? So we've created a sigma bond here. Right? So we have a sigma and a sigma star. Right? And so here the PZs have now formed a single bond. Right? It's a sigma bond through the bond, right? That's the single bond through the internuclear axis of the nitrogen. Now let's think about the off-diag, the other ones. Right? We also have 2px plus 2px, which is the same, of course, as 2py plus 2py. Right? Those are going to be perpendicular to the bond. We've got two atoms like this. Again, I'm using different colors. I apologize. Right? We've got polarity or phase, positive and negative. Right? Now what we can see is a slightly different bonding motif. Right? This is going to overlap constructively above the bond and below the bond, but not in the middle. It's form kind of like a hot dog bun structure, where the positive overlaps constructively and the negative lobe overlaps constructively, but we create a nodal plane or a nodal line here where there are no electrons. So this looks a little different than the sigma. Right? In fact, if we rotate 90 degrees, we don't have the px orbitals anymore. Now we have the py's. So these don't have spherical symmetry. Instead, they just look like a two-dimensional hot dog bun sitting that's putting the internuclear axis through the slit in the hot dog. And there's nothing, and if I rotate it 90 degrees, I end up in a different set of orbitals, the p-axis. And so these aren't spherically symmetric anymore. But they do overlap across the bond. This is a bonding interaction, but it's not sigma, because it's not spherically symmetric anymore. Right, so we have a new name for these, right? These have, remember that we use sigma, when we talk about molecules, we promote SPDF to sigma, pi, delta, and I forget what F is. Epsilon, I forget. So we up sig, I forget what it is, delta. I don't know if delta is D. But anyway, we take from SPD, we go to sigma, pi, and delta. And so these have the symmetry of the p orbitals, right? The p orbitals have lobes above and below, but not in the middle. And so we call these pi orbitals. So this is what's called a pi orbital. Right? And pi orbitals, right, we have two of them, right? There's the px's, but there's also the py's out of the plane, which I'll just kind of draw in a different color. Right? We have the px's on this plane. And they form exactly the same interaction, but perpendicular. And this is px. So what we do is we get two equivalent sets of p orbitals. We have the x ones and the y ones. There's a degenerate set. So these are what we call doubly degenerate, which means there's two of them and they're the same energy. Okay, and so what we would get now is a set of a pair of bonding orbitals and a pair of antibonding orbitals. So this is my pi star, and this is my pi. Combine all of mine. Now we also have to ask the question, does Z and X combine? And the answer is no, because they're perpendicular to each other. We don't even have to worry about the off combination. They don't even mix. Right? And you can see that by drawing the x orbital in this direction, and then the z orbital in this direction. This is green. And so what we get, if you think about how these combine, bond cuts out, you get a positive interaction with a positive interaction. So that's plus plus, but then you get the negative equivalent on the other side. And so this whole integral is zero. Right? All the positive overlap gets canceled out by the negative overlap on the other side. They don't mix at all. So these are the only sets of orbitals that we get. It's the X combination of the p orbitals and then one set of sigmas. Right? And now we can fill in our sigmas. Right? We have 4 electrons left. So they just slip into the pi orbital. So, oh, sorry, I put these in the wrong place. I'm sorry. Sorry, let me go back. This is the 1s. So these are in the 2p's. I apologize. I didn't know where I was looking. All right, let me put these up here. They're up here. There we go. And these are our pi and pi star. Okay, so we have, again, 2 new bonding interactions. All right, we have 2 fully filled bonding molecular orbitals. We now have 3 pairs of bonding molecular orbitals. So the bond order for this is 1/2 times, remember, the bonding minus the antibonding. These contribute 0. These contribute 0. And we're left with 6 bonding electrons and 0 antibonding, which is 3. Right? This is a triple bond. Okay. The triple bond forms with a bonding sigma combination. That's the single bond through the axis, and then 2 perpendicular pi bonds that form the double bond and the triple bond of the system. Okay, so that's nitrogen. Now, one thing that I don't know, and I've just made an assumption, is that the sigma is more stable than the pi. I don't know if that's true or not. I'm just guessing. I don't know which way they are. There's somewhat of an ambiguity. But we should also think about the fact that the 2s electrons, we haven't even considered these. Right? These are fairly close to the p's. They're a little further away, but we could say that they probably mix a little bit. So the s's, the two s's, they're not going to stabilize. The two s's are not going to stabilize the pi orbitals because the 2s orbitals are spherically symmetric, and it's just like the 2pz plus the 2px. The 2px is going to cancel out with the sphere because it's positive on both sides, and the p orbital changes signs. So that's not going to work. But the 2s orbital does combine with the sigma orbital. So there should also be, I'm just going to kind of roughly draw it, some interactions between the p orbitals and the s orbitals, where those s orbitals also mix a little bit with the sigmas. And so what that will do is cause the sigma orbital to become even more stable. And so the more overlap you get, the more stable a bond is going to be. Remember, that's the most important part, is the overlap. So when I bring in another orbital, I've got some other orbital with some electrons that can mix with another one. I'm mixing more and more orbitals together, and so the molecular orbitals I create become more and more stable. I always want to mix things together to stabilize. That's the whole point of bonds. So what we see, let's look at this trend and these orbitals and their energies as a function of the different atoms in the period. Right? We want to look at things along the octet. So as we move along the 2p, the octet, n equals 2 octet, go along the p orbitals, we're going to go from boron to carbon, to nitrogen to oxygen to fluorine. We're adding more and more electrons to exactly the same molecular orbital combination. The orbitals look exactly the same for all of those homonuclear molecules. So disodium, diboron, dicarbon, oxygen, nitrogen, fluorine. They all have the same combinations because they're all made up of the same orbitals. But the key difference is that the energies of the atomic orbitals change as we add and remove electrons. So the orbitals are going to mix differently depending on the atom and the repulsion of the electrons in the valence. And so they will all look like this qualitatively, but the ordering is going to change based on how many electrons are in the valence. So let's look at a picture of that. And this is kind of a nice periodic trend that we can pull from this information. That's not what I want. Let me erase, well, this is already covered a little bit, but so what I have here is our homonuclear diatomics along the octet, right? We go from lithium to dilithium. If you're a Star Trek fan, you know, dilithium to fluorine, right? And I have the orbitals and the n equals 2 valence arranged here. We've got the 2s sigma bonding. This is the 2s antibonding. This is the pi orbitals. This is the sigma from the p's, and then the pi star and the sigma star. And you can see that as we start to add electrons in the valence, the mixing in the orbitals energies, they're all the same, but the energies start to change, right? They start to become more and more negative. Like everything starts to drift more negative as we go down the periodic table. But notice that it depends on which orbital you're in, that the trends of how the energy changes. Notice that as in the 2s orbitals, as I go up the system, or sorry, as I go up the periodic table, what am I doing? I'm adding more and more protons into the nucleus, right? So the nucleus becomes stronger and stronger here. The nucleus grows in this direction. So that means that the positive charge is stabilizing the electrons even more, pulling them in deeper, right? We see that in the core, right? The 2s electrons are the closest to the core in the valence, and we can see a massive change in how much they get stabilized because of that attraction of the proton or the protons, right? So this is nuclear attraction pulling these down. Right? And we can see that also in pretty much all the sigma orbitals, right? This one also declines by the same amount, right? And the sigma bonding orbital also declines, right? So we see significant declines in energy with the s orbitals as the nucleus gets bigger. But now notice the pi orbitals. Pi orbitals hardly change at all as you go. Now, why is that? Very little change along the pi's. Well, the reason why that is that those electrons have been polarized out of the bond axis. They've been pushed out, and they're orbiting the system outside of the bond axis. And so those electrons are very far away. They're the furthest electrons from the system. So they experience the least positive charge. They're the most shielded from the nucleus. And so as the nucleus gets bigger, those effects of the positive charge are essentially quenched in those electrons. So these electrons are orbiting fast enough that they're effectively immune from those changes. So L equals 1. It changes what I would call nuclear immunity. Right? They just kind of look like hydrogen electrons. They're just constant because the nucleus doesn't look very much different to them as you increase the number of protons. They're very shielded by the inner part of the atom. So notice what happens. So in nitrogen, the pi orbitals are more stable than the sigma, which is opposite of what I wrote. But as you start to get to oxygen and fluorine, they swap. Right, so the sigma and the pi swap at the end of the valence. And notice what that leads to. It puts the final 2 electrons in oxygen unpaired in that pi star orbital. No, that is pi star, I'm sorry. Right? In oxygen, because of the way that the stabilization works, you end up having a system where the orbitals are half filled. Now this means, notice in nitrogen we have a bond order of 3. All the bonding electrons are filled up, bonding orbitals are filled. Now we have 2 anti-bonding electrons in oxygen. That means it has a bond order of 2. It's a double bond. Right? This is a bond order, so the bond order. Right, let's look at what the bond order may be for these. Here there are only bonding electrons, so the bond order is 1 for dilithium. Look for beryllium, the beryllium dimer. Both of the anti-bonding and the bonding are removed or cancel each other out. So from this perspective, the beryllium dimer has no bond. Turns out it does have a bond, but it's very, very weak. And MO theory can't predict it. It's a different story. Now look at boron. Boron has 2 unpaired electrons. It has a bond, but it's a triplet. It's a triplet. It has 2 unpaired bonding electrons. So it's magnetic. Carbon. Turns out dicarbon is kind of weird. Generally, we argue that it has a bond order of 2 or 4, depending on how you look at it. But we can say it has 2 from this perspective. Nitrogen has 3. Oxygen has 2. It's also a triplet, meaning oxygen is magnetic. And fluorine has a bond order of 1, right? It's a single bond. So the bonding characteristics of the octet just come from the way that the microorbitals are filled. Right? And the behaviors of some of the weird molecules like boron, diboron, and dioxygen just the fact that oxygen is magnetic because it has two unpaired electrons, is born out of this arrangement of the orbitals. It's just a consequence of how the orbitals align. I want to show you, let me see if I can find a video of it. I want to show you that oxygen is in fact magnetic. It's one of those things that we don't really appreciate because you don't, in a gas phase, oxygen is moving around randomly enough and dispersed enough that it doesn't really have a strong magnetic force. But if you condense oxygen into liquid, the spins align in the liquid and cause the liquid to be magnetic. So let me see if I can find a picture of this. Almost certainly Nile Red has done this. Is this Nile Red? I almost think this is. No, it's not. Tommy Technetium. What a name. All right, so here's a picture of liquid nitrogen poured between the poles of a magnet and liquid oxygen being poured. So here's liquid nitrogen. It just flows right through like nothing. So permanent. All right, nitrogen is a singlet. Now here's oxygen. Can you see that? That's not the best picture in the world, but you can see that it condenses right in the middle. It doesn't just pour right through. There's a small amount. There you go. Right, that liquid oxygen gets stuck there because oxygen is magnetic. Right, it evaporates very rapidly because it's liquid oxygen and we're at room temperature. But I actually had this is one of the things that really inspired me as a high schooler. My high school teacher, he took liquid oxygen and put it on the table like this. And then stuck a couple of like cheap little hockey puck magnets on it, and they sit there and they float up and levitate. It's really cool. Okay. So again, molecular orbitals give us these properties, come entirely from the molecular orbitals. Okay. All right, so let's take this idea and try to apply it to something a little more interesting than just the heteronuclear diatomics or the homonuclear diatomics. Let's think a little bit about the heteronuclear diatomics, like HCl. Let me pull my notes up for this really quickly. So what about electronegativity? Right, how does that influence the orbitals? Let's look at an example molecule. Right, an example. Let's look at the molecule NH, which is a radical, diatomic molecule, radical. Now let's do the analysis exactly the way we did it before. Right? How do the orbitals combine? Well, we know that the 1s1 of hydrogen is at minus 13.6. The nitrogen 1s1 orbital, we don't even care about, right? It's at 100 eV. Sorry, 1s2. Nitrogen 2p, or sorry, 2s2 at minus 18. And the nitrogen 2p3 is at minus 12. Right? So let's think about how N and H will combine, right? The 1s orbital of nitrogen had nothing to do with anything. It's just sitting by itself at the bottom, right? There's no mixing, right? There's not even another 1s core valence or core orbital for it to mix with. So down here at the bottom of our energy diagram, E, let's do the same construction we did before, where we put nitrogen here and hydrogen here and NH in the middle. We have minus 100 eV. We have this 1s2 state, right? It doesn't combine with anything. Hydrogen doesn't show up till 13. So this orbital just gets progressed over. It's just that it doesn't mix with anything, right? So we create an orbital here that just has entirely 100% S character. 1s2 character. Right? It's not a bonding orbital, it's just an atomic orbital. It's just sitting there by itself. Right? That orbital in the molecule is just nitrogen's 1s2 orbital. So we call this a non-bonding orbital. Right? It's one where beta is 0. Right? Where the atomic orbitals don't mix with anything, they just sit there. I want to get this diagram up out of the notebook. Right, so the interesting wave functions, of course, are the interactions with the family. Now, the fact of the matter is that the s orbital in nitrogen just really isn't going to interact at all with the hydrogen one. It's too deep. So at 18, we have this 2s2 orbital, and it may mix slightly with the 1s orbital of hydrogen, but by and large, we can just ignore it. Right? So we're left now with a set of orbitals, p orbitals at 12, and at minus 13, at 14, but these are all minus numbers, I apologize. Minus 14, we have the hydrogen atom, 1s1. Right? So the question now is that this is the predominant interaction between these two orbitals. They're the closest together. But the question is, how do they interact together? But we know roughly what they should do, right? Because the p orbitals that are perpendicular to the bond, the x and the y's, they cancel out any spherically symmetric thing on the other side. Right? Again, we don't have to worry about 2px plus 1s or 2py plus 1s have beta equals 0, right? Because the orbitals look like this, and through the bond axis, we have a positive contribution and a negative contribution, and the total is 0. So the only contribution that we have is the pz in the 1s, where there's sigma. Right? So 2pz plus 1s is the only bonding contribution. Right? Because we get something that looks very clean. Right? Through the bonding axis, right? We have the plus and the plus, and they combine to form a sigma and a sigma star combination. Right? But the energies of them are slightly different. And so beta is not going to be very big, because they're slightly different energies. Beta is going to be smaller than when you have two states that are the same energy. So they're not going to stabilize and destabilize quite as much. So what we would expect from our molecular orbitals is that we get two non-bonding orbitals, which are from our px and py. Right? And then we get a very slight mix of 1s and 2pz, where beta is small, so the shift is small. Right? So I'm going to have a sigma bonding orbital here, and then another sigma bonding orbital, sigma antibonding here, that looks more like nitrogen. Okay, and so now the question we have to ask is, what do these orbitals look like? Well, they're going to look more like the atomic orbitals that they're next to, that they're closest to. So this sigma bonding orbital looks very hydrogen-like, right? Because it's close. So this is so we would say that this is very hydrogen-like. So it's close to 1s. So this is polarized towards hydrogen. Right? We would expect the bond in some sense, if we have the nitrogen here and the H to be here, that the orbital is wide, and then it kind of polarizes around the H instead, and less around the N. Right? So we get a lot of negative charge buildup on this side because the electrons are sitting closer to the hydrogen. Now, what does the antibonding combination look like? Well, that's going to look more like nitrogen. So the antibonding combination will have a bigger lobe on the nitrogen and a smaller negative lobe. I'm sorry, I need it to be on the other side, on the hydrogen, right? And so this is polarized towards N. Okay. So what's total? Actually, so in reality, this is not a single radical like I've drawn because there's two unpaired electrons in this. I haven't filled the orbital yet. So we have a single bond here, right? But in fact, I have two unpaired electrons. This is a biradical, right? So I would put another radical there because I have two free radical electrons. Okay. And the important thing here is that because of the electronegative, because of the way that the bonds are polarized, look at the bonding interaction, these electrons, right? The predominant electron density is on the hydrogen. It's just telling me again that you would think again nitrogen is a polarizing atom. It's electronegative, wants to pull electrons away. But the way that this biradical is constructed, all the bonding electron density is actually on the hydrogen. So the hydrogen is negatively polarized in this. It's a basic hydrogen, not an acidic hydrogen. Right? It's polarized towards the H, not the N. Now, if we go, now interestingly, if you add another hydrogen to this, you form another combination, bonding combination with one of the other p orbitals. And so then you only have a single radical, and then you make ammonia, which is NH3, and then what you end up having is a lone pair on the nitrogen once you combine everything. There's two electrons that don't contribute in ammonia. And there, then the polarization of those electrons now is on the nitrogen. So in ammonia, the nitrogen is basic, but in H, the hydrogen is basic. All right, so electronegativity is kind of a tenuous concept. Very generally, with well-behaved molecules, where everything is paired, the electronegativity trends are correct, right? Fluorine tends to be more electron withdrawing than oxygen, which is more electron withdrawing than nitrogen, nitrogen, and so on. But that really depends on the structure, the electronic structure of the molecule. Because here's an example where nitrogen, in fact, is the acidic part. It's more than happy to take an electron. Right? It wants to fill these orbitals. So it's going to take an electron. The nitrogen is acidic. This one wants to give things away. Now, notice what happens if I excite this electron from sigma to sigma star. Then the polarization starts to go on the nitrogen, and in that excited state, the nitrogen acts like a base. So the electronegativity isn't always a good tell, and especially if radicals think, and hydrogen in particular can act particularly funky and be very, very basic, because it's just a really easy place to put electrons in molecules where there aren't really any good places to put electrons. Hydrogen is more than happy to accept them. So again, this comes from the things that we learned in organic chemistry, that hydrogen can both be an acid and a base. And here you're seeing it as a base. Okay. I think I'm going to do Huckle this year. Right. I want to just show you an example. So what we'll do next class, talk about methane in particular. We're going to talk about hybridization. I want to show you an example of hybridization. I want to look at ammonia. Right. Let's just take this example and now add 2 more hydrogens. And I'm not going to. Now we have a complicated structure, right? Because ammonia has this methane-like structure. It's got 3 hydrogens and an umbrella and a lone pair sticking up. It's non-planar. It's not so obvious how we combine the orbitals together, because now they're not all like on a line 90 degrees to each other. It's very easy to add things. Now we've got things at angles and different combinations. It's a little more complicated. Right, but I want to see if I can use some rules and use some of the ideas of the to come up with a way that allows us to think about ammonia in a simpler way than just about 4 atoms adding together. So what do we know about ammonia? The most important thing about ammonia that we can take advantage of is that each of the hydrogens are exactly the same. Right? So we know that this is 3 equivalent NH bonds. And the other thing that we know is that if we look at nitrogen from bird's eye view, the hydrogens form 120 degrees. Right? It's an equilateral triangle. Right? It's a trigonal pyramid, right? The 3 hydrogens are like this, and nitrogen is here. Right? So we have this nice symmetry. So these hydrogens, we can combine them together. We can say, instead of saying we have 3 independent hydrogens, we have one set of 3 hydrogens. We combine them, so we hybridize the hydrogens together. So let me call these HA, HB, and HC. And what we're going to do is think about NH3 as combinations of the nitrogen atom plus a combination of our different hydrogen atoms. So this is what we call a hybridized set of orbitals. Right? We're going to add them all together because they're all equivalent. You can think about them as a sum of set, as a trio. Right? Now, to understand, we have to think about what these wave functions for the trio look like. We're adding 3 wave orbitals together, so we should get 3 hybrid orbitals out. Right? Remember, we put in XAOs, we get XMOs out. So we're putting in 3 AOs, we should get 3 orbitals out. Okay, so we have, so hybridization says in atomic orbitals, I get N, what do they call it? N hybrid orbitals. All right. Now, to figure out which are the 3 is a little tricky. You have to use a little bit of max symmetry now. But let's think about it like this. We know that the ideal combination of wave functions, the lowest energy combination, is just going to be the plus of all of them. Right? I just add them all together. So psi1 plus psi2 plus psi3. That's always going to be the most stable arrangement. So I'm just evenly adding them all together. So I know that at least one of my hybrid orbitals looks like psi HA plus psi B plus psi C. And what else do we have? I'm sorry. And then we have the anti-bonding combination, which is psi HA minus psi HB minus psi HC. All right, what do those look like? Well, I could just draw them like little circles, right? I have one that looks like this. Okay, and we get interactions between all three. That's great. That's why this should be the most stable form. And then we get an antibonding orbital where the sign changes each time. So we get an antibonding orbital here. This is a sigma star, and then we get a sigma combination between the two. So those are our that's our antibonding and bonding combination. That's one of our hybrid orbitals. And then we have two more to deal with. It turns out that the other set, right? So this has 0 nodes. So the other set's going, and the worst combination has 2 nodes. Okay, so that means that the next best combination should have 1 node. 1 node. And so when you do the math, and this is something that you work out in organic chemistry, that hybrid number 2 and 3 are identical. There's 2 different ways to form combinations with 1 node. One of them or with 2 nodes is this one. We have a plus and a negative. That's 2 nodes. And then you have another one where you don't have any contribution on this atom. And then you have a plus and a negative like this. All right, so these are our other ones. Did I get this wrong? 1, 2, 3. Well, there's more than this, actually. There's multiple nodes in the middle here. So there's 4 nodes here. I apologize. There's 4 nodes here. There's one in the middle as well. And here we have 2 nodes. There's one here, one here. There's a node here between these, and this is a node. So what happens is the hydrogens combine into 3 combinations. Right? We get 3 AOs, we get 3 MOs out. So I'll go ahead and write that. So let's go ahead and draw our diagram. So here's our 3 H's, and here's our nitrogen atom, and here's NH3. All right, I'm just going to skip the 1s because we know that the 1s doesn't matter. Right? It does not contribute at all. All right, so we'll start at minus 18, right? We have the 2s orbital. And then we have at 12, minus 12, we have the 2 p's. And then at minus 14, we have 3 orbitals for our hydrogens, right? We have 3 orbitals. We have 1 and then 2 that are the same, right? One of these is the one that they're all combined. And the other one is the ones with the nodes. Oh, right. And how are those filled? Get 2 in here. And then 1 in here. Oh, sorry, these are all, sorry, they each bring 1 electron, so they each have 1 electron. This. Right, how are things going to combine? Well, let's think about what the 2s looks like with these orbitals. Right? So 2s2 plus 3h. Right? We have this nitrogen in the middle. Right? This is our 2s orbital for our nitrogen. And then we have 3 oxygens or hydrogens separated at 120 degrees. Right? And I get a combination that looks like this, right? And this is perfectly fine, right? We form a combination where those 2 add, right? In a constructive way. Orbitals will add. So I'm going to get a combination between the 2s, 2, and the these destabilize just a second. And then slightly above energy, I'm going to get the antibonding combination. We'll call that 2 sigma and 2 sigma star. Right. Okay. And so these fill up. That one fills up. All right, what about the other combination with the doubly degenerate ones? Well, let's look at that. You get something that looks like this. And so this cancels out. I'm sorry. Sorry, I need to put the other one. Sorry, this needs to be a dot here. Right, and which is no interaction. And this one also does not work, right? Because they cancel each other. So we have a positive combination here and a negative combination here. So the net combination is 0. So the other 2 orbitals of the hydrogens don't interact with 2s2. They cancel out. So it only interacts with one of them. All right, we're left with now the combination of the hydrogens with the p orbitals. Okay, and so what do these combinations look like? Well, one of them is going to look like this. That combination, right? That's going to be the symmetric combination of the hydrogens plus one of the p orbitals. Notice that this one has no net bonding interaction, right? Because each of these atoms interact with the top lobe and then cancel out with the bottom lobe. Right? So the even interaction does not interact with no bond with this 2p orbital. Right? So I'm going to create a new combination right, that is effectively non-bonding, which is this combination here. Right? And then we have these interesting orbitals where they're sideways, right? We have the nitrogens now that are in the plane. Like so. And the best combinations that these have one combination is going to look like this. Like that, where we have positive interaction between these lobes and positive interaction between this hydrogen and the lobe in the back. So that's nice. That one works. We also have another interaction where the p orbital is perpendicular to that, where I have a hydrogen like this, and a node here on this hydrogen. And again, we see positive interaction between these two. Right? So I form a bonding combination between the other 2 p orbitals and these sigma orbitals. Those hydrogens. So I form a pair of pi-like orbitals. I gotta forget the antibonding orbitals. Right? Where I get pi and pi star. Like that. Okay, and then we just have to fill up electrons. So they fill up like that. So what do we have? We have 3 bonds, 3 sigma bonds. Sorry, these are sigma. I apologize. These are sigma because they're aligned with this. If I rotate, we draw the axis. If I draw it like this and I rotate around here, it's the same. So these are sigma. Apologize. Right. So I've got 2 sigma bonds, and this right here is a non-bonding. This is our non-bonding. Right. So I have a set of unpaired electrons and a non-bonding orbital that are sitting above and below the plane of the molecule. So I have a lone pair sitting above and below the nitrogen, the hydrogens. Right? And then I have 3 sigma bonds between the hydrogens and the nitrogens. So what the total result here is 1 PZ lone pair and 3 sigma bonds between hydrogen and the 2px and the 2py orbitals of ammonia, nitrogen. Okay, so we would therefore expect the structure of this molecule to be nitrogen with 3 equivalent bonds to hydrogen, and a non-bonding lone pair that are outside, pointing up in the z direction. So I've kind of hand-waved some of this work, right? I haven't convinced you that the orbitals will combine in these orientations, but that's how the symmetry map ends up working when you do what's called point groups theory, which you'll learn in organic or in my spectroscopy course. But you get these combinations and they're exactly the same energy. And we're going to see similar types of behavior in methane. In methane, we're going to have 4 equivalent hydrogens, all at 109.5 degrees relative to each other in a tetrahedron. So we'll be able to construct hybrid orbitals of hydrogens together in the same way, but instead of using an equilateral triangle, we'll be able to build it in a tetrahedron. And so we'll look at that next class. Okay. So that's molecular orbital theory for now. So we'll finish up some advanced stuff. We'll basically rederive organic chemistry from the ground up next class. And we're done.